Welcome to this explainer. Today, we're diving straight into Chapter 2 of the MMDSF framework to tackle a massive, fundamental mindset shift in how we approach time series data. We are moving way past the basics of just processing signals, and we're stepping into the real art of forecasting judgment.
Okay, so let's dive into this provocative question. Can a complex model actually manufacture information? Let's be real for a second. It is incredibly tempting to just grab the latest algorithmic heavy machinery, things like deep learning or light GBM, and throw it at your data just hoping it'll magically find a hidden pattern. But why is this such a common trap for us? Well, because we desperately want to believe the model can find something that we can't. But the hard truth, before you spend hours, or let's be real, days or weeks tuning a complex model, you absolutely have to measure if there is actually a forecastable signal present in the first place. It's the classic garbage in, garbage out scenario, but elevated. A complex model literally cannot manufacture information that simply is not there.
Section 1. The Forecasting Illusion. We're going to start treating our data like patients walking into an emergency room. To do this right, we need to perform a crucial triage before we ever prescribe a treatment. Take a look at these three specific synthetic series. They present vastly different challenges in the real world. We've got smooth demand on the left, displaying clear, readable patterns. Think of this like daily sales of milk at a grocery store. Super predictable. In the middle, intermittent demand, where the data's sparse and zeros are common, more like selling specialized spare airplane parts. And then on the right, near noise, which is almost entirely random and chaotic. Now here's the kicker. They all share the exact same forecasting horizon, yet they represent entirely different levels of difficulty. If you apply the exact same massive machine learning strategy to all three of these without checking their vitals first, you are absolutely setting yourself up for failure.
Moving on to Section 2. What is forecastability?
So what actually makes a dataset predictable in the first place? We need to be highly disciplined with our language here. The crucial point you need to take away is that a forecastability score isn't some universal magic number that's permanently baked into your series. Not at all. It is entirely dependent on the context. It changes based on your specific forecasting horizon, the data transformations you apply, and the loss function you choose to evaluate it. Think of it this way. If you look at daily sales data for umbrellas, it might look like pure, unpredictable noise. But if you change your transformation and aggregate that exact same data on a monthly level, suddenly, boom, a crystal clear seasonal pattern emerges. Forecastability is not a single metric. It's a highly contextual diagnosis.
Section 3. ADI-CV² Demand Quadrants.
To actually measure this context, we need specific diagnostic tools, right? And we begin by classifying our demand. The ADI-CV² quadrants are a brilliantly effective way to categorize the severity of our data's unpredictability. Let's break those acronyms down. ADI, that's the average demand interval. Basically, how much time passes between sales or demands. Are people buying this every day or just once a month? Then we have CV², the coefficient of variation squared. This is just a mathematical way of measuring the volatility. How wild are the spikes in volume when a demand actually happens? By mapping the time between demands against the wildness of the volume, we cleanly divide our series into 4 distinct profiles: smooth, erratic, lumpy, and intermittent. This framework completely stops us from treating a lumpy, highly unpredictable series with the same assumptions we'd use for a smooth, highly seasonal one.
Section 4. Variance Ratio and ACF.
Okay, so taking that ADI-CV² measurement, that's like taking the patient's pulse. But we also need an MRI to look deep into the internal structure of the signal. ADI-CV² answers our questions about demand classification and timing intervals. But the variance ratio and the autocorrelation function, or ACF limits, do something entirely different. They are the deep diagnostics that reveal if there is actually a predictable structure hidden inside all that noise. They test the very limits of our signal's memory. Autocorrelation, for example, tests how much past data relates to future data. If what happened last Tuesday tells you absolutely nothing about what will happen this Tuesday, your ACF will expose that total lack of structural memory. These metrics answer entirely different questions from our demand quadrants, and you honestly need both for a complete, honest diagnosis.
Section 5. The Forecastability Dashboard. Instead of running all these tests manually and getting completely lost in the math, we can synthesize these diagnostics into a clear visual anchor. The MMDSF Pro dashboard is designed with intense focus. Notice how it evaluates just 3 to 4 key measures? Why is this such a lifesaver? Because anyone who has worked in data science knows the absolute pain of being overwhelmed with 12 different metrics that all conflict with one another, leaving you completely paralyzed and unsure of what to do next. More importantly, This dashboard is emphatically not a black box score. It's a practical, entirely transparent screening workflow that distills exactly what we need to know and directly guides our model family recommendation.
And finally, Section 6. Choose your strategy last. Only after we've run this compact triage on our synthetic series do we actually decide on the treatment. This clear decision flow shows the true power of the framework. Step 1, diagnose. Step 2, classify. Step 3, route. Let's actually walk a data point through this journey. Imagine the relief your team feels when the smooth demand series naturally routes toward a powerful but standard machine learning model or even a simple ARIMA. No guesswork needed. Then the intermittent demand series gets routed to a specialized intermittent model built to handle those zeros. And most importantly, we have a highly specific routing for that frustrating near-noise series we saw at the very beginning.
I absolutely love this next part, and it might just be the most liberating takeaway of the entire framework. You literally have permission to abstain from forecasting. If your dashboard screening shows that a series is pure noise, the scientifically and mathematically correct modeling strategy is to do nothing. Abstain. Walk away. Do not waste your time, your expensive compute resources, or your sanity trying to force a complex deep learning model to memorize random chaos.
Which brings us to the core thesis of the MMTSF framework's entire diagnose before model cluster. Before you tune a model, measure whether the data contains a forecastable signal. Model choice comes second. It is a fundamental shift in priority. The diagnostic workflow is the true heavy lifting here. Prioritizing this diagnosis is an absolute game changer for your resources and your peace of mind because honestly, the algorithm you eventually pick is just the final mile. As we wrap up this explainer, we've successfully laid the groundwork for assessing predictability. In our upcoming topics, we're going to dive even deeper. We'll be exploring entropy and Lyapunov exponents, and we'll break down exactly why you should stop using MAPE for good. But until then, I want you to ask yourself this critical, provocative question before you write your next line of code or build your next pipeline. If your next complex model fails to deliver results, are you going to blame the algorithm, or will you realize you skipped the triage?